Hello everyone! Since I'm not with you and some of these were on the test last year, I wanted to make sure that you knew what the answers were. So let's talk about number 7. Number 7 is saying there's a series that goes from 1 to infinity of a whole bunch of numbers. So notice there's no x, it's not a power series, it's just a regular series. And I know this infinite series converges to 10, and that all of the numbers in the series are positive. So now the question is, which of the following things must be true? So this first one is true. It's saying the limit as n approaches infinity of the nth term is 0. So in other words, that's just saying that all of the terms in your series are approaching 0. So why might this be true? Well, if you imagine that the limit as n approaches infinity doesn't approach any finite value, then that might be the same thing as all of your terms increasing without bound, in which case it's failing the nth term test and it's obviously diverging. It can't be the case that they're decreasing without bound because we know that all of the terms are positive. It might, however, be the case that the magnitude of the terms is approaching a value that's not 0. Like what if, for example, they were all approaching 1? In that case, you could sort of imagine graphically, I've got a bunch of values and they're asymptotically approaching 1. And if you want to imagine your sum as if it's a rectangular approximation of an integral, we're going to be adding up a whole bunch of area here that's some non-zero height above the x-axis. And so clearly that's also going to diverge because there's an infinite area that we're going out this way for. So that one's true. Okay, let's take a look at this one. So limit as n approaches infinity of s sub n equals 0, where s sub n is the nth partial sum of s. This was one of the main points of this question, was do you know what a partial sum is? So remember how we defined a partial sum. If I've got my series with a whole bunch of numbers going from a sub 0 out to, I guess we started at 1, didn't we? Okay, starting at a sub 1, going out to a sub whatever. S sub 3 would be the partial sum of the first 3 terms in my series. A sub 4 would be the sum of the first 4 terms in my series. So if I'm looking at the partial sums as n approaches infinity, that's like saying, let's look at the sum of the first n terms in my series where n approaches infinity. And that's the same thing as what my series is eventually converging to. So this value right here, the limit of my partial sums, I know is equal to 10 because it said so up here. My series is converging to 10. So it can't equal 0 because this would imply that my whole series up here was converging to 0. So this one's false. All right. So what if I take every single term in my series and I multiply it by n? Does that mean it's diverging? Well, you might think, yes. You might think, so I've got a whole bunch of terms. I've got a1, a2, a3, a4. So if I'm multiplying each term by n, that's like saying 1, and then 2, and then 3, and then 4, out to n, a sub n. So if I just look at this, it kind of feels like it might diverge. But think about all the different things that these a sub n terms could be. For example, what if a sub n is defined as 1 over n cubed? So then I've got a series that is the sum of all the 1 over n cubes. I could multiply it by a constant on the outside so that I'm sure it still converges to 10. So that satisfies all my conditions up here. But notice that if I multiply each of my terms by an n, that's like doing this, and that's going to give me 1 over n squared, which still converges. It's not going to converge to 10 anymore, but it's still going to converge because it's a p-series where the exponent down here is greater than 1. So just because we're making each term larger doesn't mean it's going to diverge. So this one's false. Okay, what about this one? So what if we take each of the terms in our convergent series and we divide it by n? Well, one good way of thinking about this is I'm taking all of the terms in my convergent series and I'm making each one even smaller. So there's no possible way that that's going to make the series diverge because it's already convergent and I'm just making all of the terms smaller. So that one's true, it's going to converge. Okay, what about this one? So here I'm starting at n equals 10 and going out to infinity, and I'm multiplying them all by 3. Well, this hasn't really changed anything important about what was making the original series converge. So if my original series converged, starting at the 10th term, it's still going to converge, because I just cut off whatever sum those first 10 terms are equal to. And then multiplying the whole thing by 3 is just going to triple the value that it converges to. But it's not going to make it diverge. So that one's true. Last one. So this would be true if this one was an alternating series. That was that error bound for the alternating series. So here I'm saying the distance between the nth partial sum and the actual value of the sum. So this is another way of describing the error for the nth partial sum. So I'm saying the error for the nth partial sum is smaller than or equal to the magnitude of the next term. And that's exactly what we ended with last time as the error bound for an alternating series. But the problem is this isn't an alternating series, so this rule doesn't apply. But it would apply if it were an alternating series. For this problem, g is a function that has derivatives for all orders on all real numbers, and then it's telling us what are the values of the function and many of its derivatives evaluated at x equals 5. And so now it's asking us to write the fourth order Taylor polynomial centered at x equals 5, or around x equals 5. So remember, the nth term for a Taylor polynomial is the nth derivative evaluated at the center over n factorial. So that's the a sub n coefficient. And then the term itself is x minus the center to the nth power. So in our case, the center is 5. So all our terms are going to be some number times x minus 5 to the n. And then we just need to know what are these function derivatives evaluated at 5. But those are all given to us here. So if I'm going to write out the first, how many? The fourth order Taylor polynomial. So if I'm going to write out a fourth degree Taylor polynomial, here's what it looks like. All I did was I just took what is g of 5, what is g prime of 5, what is g double prime of 5, and so on, and plugged those in as my derivative values up here. And then for each term, I divided by n factorial for whatever the term was. So there's 2 factorial, 3 factorial, 4 factorial. And then I have x minus the center to the nth. So there we go. So part B asks for the third order Taylor polynomial of the second derivative of g. Well, I've just written, what was it, a fourth order for g. So what would happen if I took the derivative of this one twice? I'd take the derivative of each term, and that would give me some approximation of g double prime. The problem here is if I'm starting with 4, I take a derivative, that's going to give me a third degree and then a second degree. But I need a third degree. So let's write out one more term here on the end before we take the derivatives. So my last term here will look like this. So notice when I take the derivative, this constant drops out. If I had distributed this, I would have negative 2x, and then I'd also have another constant, which would have dropped out. And so the derivative of my negative 2x is just negative 2. Here, the 2 comes down, and I've actually... Okay, so in this one, I've canceled it already. So here, the 2 is canceling with the 2 factorial in the denominator. For these ones, I didn't cancel yet, so let's just look at them. The 3 will come down, so I'll have 12 times 3 divided by 3 factorial. So if you have 3 factorial and you're only canceling that top number in the factorial, what you have left is 2 factorial when you cancel the 3. Here I've brought down the 4, so now I have 4 in the numerator and I have 4 factorial like I did originally in the denominator. And again, I'm canceling the 4 with the top number in the factorial, so that gives me 3 factorial. And then same thing here, that would give me 4 factorial. There. So now all I have to do is take one more derivative. And there you go. So I'd say the key for this problem was just at the very beginning, thinking about how do I get to what I want from what I have. And like I said, you're sensing this is a common theme in all problem solving. So we wanted g double prime before just going ahead and starting to try and think about applying the procedure that you'd been shown. think, what information do I already have that would have been useful? And the answer is, oh, if I've got g, that'll help me find g double prime more easily. Let's look at this number 5 real quick. Just intuitively, this one should converge, diverge, converge, 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 diverge. Let's look about y real quick. So your first thought might be that n factorial is a much larger order of growth function than 8 to the n, and that's true, but that's not a very safe test to use, because as we had pointed out earlier, if you had, say, n over n squared is a larger order of growth function than n, but this series would diverge because it's comparable, well, in fact, it's equal to the harmonic series, 1 over n, and we already know that diverges. So don't think necessarily about which is the numerator or the denominator of the larger order of growth. Instead, I'm going to compare this to something that I know converges, which is a geometric series. So this whole series is smaller than the comparable series 8 to the n over 9 to the n. I know that's true because n factorial is going to grow to be much larger than 9 to the n. This is the same thing, though, as if I'd written 8/9 to the n. And that's clearly a geometric series with our multiplicative constant there, our r value, as less than 1. And that's why it's a convergent geometric series. So that converges by direct comparison with a convergent geometric. Okay, so this one's sort of the same thing in reverse, only this time the n factorial is in the numerator. So it's similar thinking that applies here, only now it's a denominator. It's larger than a diverging series. Here, this one you could imagine, for example, multiplying this out, and then this is going to be directly comparable to something that's the same order of growth. It's going to be comparable to an n over an n cubed. And this is comparable to a 1 over n squared, and that's a p-series, and we know that one converges. Okay, absolute value sine n, well, the largest thing sine can be is 1, the smallest thing could be is negative 1, the smallest thing the absolute value could be is 0. So this is bounded above by 1. So I know this whole thing is less than or equal to the same sum with 1 over n squared, and that's a p-series, and that converges. Here, this is the same thing as if we had written 1 over e to the n. This one clearly converges. Again, you could compare it to a p-series, for example, n squared. So this exponent is always going to grow larger than the n squared. Therefore, the whole term is going to be smaller. Therefore, the sum is going to be smaller. This one is similar to the one above it, only with an opposite outcome. So this is going to be comparable to n over n squared, which is like 1 over n. So this one's going to behave as if it's a harmonic series, and it's going to be divergent. And a question that's going to be a really important part of what happens on Monday is about finding upper bounds for functions over particular intervals. So an upper bound is just a number where our function is guaranteed never to be larger than that number. So, for example, I might ask, what's an upper bound for e to the sine x on the entire real number line, so all real numbers? So if I'm thinking about this, let's see, x could be anything, so that means sine x is going to look like this. So sine x is bounded above by x equals 1, and it's bounded below by x equals negative 1, because I know sine x is never larger than 1 and never smaller than negative 1. So if that's true, that means e to the sine x is bounded above by e to the 1. So e would be an upper bound for e to the sine x on the interval of the whole real number. What if I ask a related question? I still want an upper bound for e to the sine x, but now it's over a more restricted interval. What if it's between negative pi over 4 and positive pi over 4? Again, we want to know what's the largest thing that this could possibly be on that interval. So sine of pi over 4, if you remember your unit circle, is going to be 1 over root 2. So what that means is that on this interval, e to the sine x is bounded above by e to the 1 over root 2. So that would be a good answer for our upper bound. You might be wondering, why have the concept of an upper bound? There's a couple of answers. One is that it's very useful in lots of different kinds of proof, but here's a more kind of concrete answer for you. Here's a tricky kind of a problem. I heard that some card dealers in Las Vegas are able to perform a perfect alternating shuffle. So you know when you shuffle your cards and they go chick, 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 chick. A perfect alternating shuffle would be a shuffle where you get one card from the left, one card from the right, one card from the left, one card from the right, just in perfect alternation. So it's a cool trick to be able to do a perfect alternating shuffle every time. So I was thinking, boy, they probably got to practice that a lot. And then I thought, I wonder if when they do the alternating shuffle over and over and over again, maybe if they started out with cards in a certain order, after a certain number of shuffles, they're back in that original order. And then I thought, well, that's definitely got to be the case, because there isn't an infinite number of different possible orderings. There's a finite number of cards, so there's a finite number of different orderings. And if you're shuffling through them, you're cycling through all those different possible orderings. So eventually you're going to come back to the one that you were at before. So let's look at the function here. If n is the number of cards in my deck, let's make a function f that says how many perfect alternating shuffles before my cards are back in the original ordering. So for example, if it were true that f of 8 equals 20, I don't think it is, but if it were true, what that would mean is if I had an 8-card deck and I was performing my perfect shuffles, if I shuffle them 20 times, now they're back in the order they started in. What I really want to know is what is f of 52. So if I've got a 52-card deck and I'm performing perfect shuffles, how many? And that's kind of an interesting question to figure out. It turns out that this is a very tricky question. And it would be nice if we had a nice equation for our answer, like f of n equals n squared over 3, or whatever it is. I mean, clearly that's not going to be it, because this isn't going to give us integers, and we need the number of shuffles to be integers. What does this all have to do with upper bounds? Well, here's what. So it would be nice if we had a function for this, but sometimes a problem is too hard for us to be able to know the exact answer. So what mathematicians do when a problem is too difficult to have an exact answer is they try and find bounds for the answer. We might not know what f of 52 is, but we might be able to show that f of 52 is definitely smaller than 52 squared or something. So that's going to give us an upper bound on the answer. And if we can put a lower bound on the answer, it's definitely greater than 52 squared minus 5. That's going to give us a very small range of possible values that the answer might be. Obviously, we would hope to find the exact answer, but sometimes putting a bound on the answer is the best you can do. It's like when I lose my keys. I would love to know where are my keys exactly, but sometimes the best I can do is put a bound on where my keys might be. It's not like my keys are anywhere. They're not in Disneyland. They're not in Japan. They're inside my house. I'm sure they're in here somewhere, so I've bounded the possible error on the location of my keys. This graph here is the output of a computer simulation I wrote to do that shuffling problem. So the computer performed perfect shuffles for decks of different sizes. So here's a deck of 7 cards, 19 cards, 52 cards is in here-ish somewhere, all the way up to 500 cards. And on the y-axis, it's the number of shuffles required to get the cards back in their original ordering. And you see what appears to be a strong linear trend here at the top. So what you could do is, if it's true that this is really linear, you could find the equation for what is this line here. And then you could say that even though we don't know what our function is, because clearly our function is bouncing around a lot in here, we do know that the upper bound for our function is going to be this line up here. So it's not like if you have a 451 card deck, it's going to take 1,000 shuffles, because we know that the number of shuffles has an upper bound of the line, and the line gives a value of less than 900. So the number of shuffles required would be less than that. Okay, so that's the concept of an upper bound. We'll be using it in a very serious way next week.